So good afternoon to everybody. Today we are super happy to having here Antonio. Antonio studied in Zaragoza, and then he moved to London, and then Cambridge, and now it's at IBM. And I can say a lot of things about Antonio, but maybe the most important is that he's building now a quantum computer. So for us, it's it's a honor that to having one of the people that are building these new machines now in the Quantum Tuesdays. So thank you very much for accepting the invitation, Antonio, and you can start your seminar.
Okay, thanks, David. I'm going to start sharing. You can tell me if you can see the presentation properly. Is that good? Yep. Okay, so I'm Antonio Corcoles, and I'm very happy to have this chance to talk today here. As David said, I did my undergrad in Zaragoza, and I finished my undergrad about 20 years ago there, and since then I haven't really had a chance to visit. So I'm very happy to have this opportunity today, and I'll be talking about characterizing and benchmarking near-term quantum computers. So let me first say what I mean by near term. We have been seeing the progress of quantum computers in the last decade or so to really accelerate as the technology became more and more mature in the different platforms. And the ultimate goal is to have fault-tolerant quantum error correction, but I won't touch any of that in this talk. I want to focus on how we can assess the performance of quantum computers, the quantum computers that we have today that are noisy and that don't provide a high level of protection against errors. The main question to us there is how do we compare one quantum computer to another quantum computer? And that's not a simple question to answer. So characterizing and benchmarking, I'll be discussing a little bit different protocols to assess the performance and what difference different ways of calibrating your operations might have in these benchmarks. So I will start by talking a bit about what are benchmarks and what are metrics. We can imagine benchmarks to comprise a set of protocols or circuits or sequences of gates that we perform in quantum hardware, and along with the analyzing analysis tools to process the outputs of those protocols, and then some interpretation of the final result. So things that we would like to require of the benchmarks is that they are device independent. They don't so we can compare different platforms using the same benchmark. That we can probe the devices at different levels, at different scales, and then that we can use the results of those benchmarks to help us develop the next generation or to improve the design of our systems. And then from the benchmarks, we can extract metrics, which are some values that the benchmark give us that have some meaning about some particular aspect of the performance. For example, you could imagine something I will be discussing later, which is called randomized benchmarking, as a protocol as a benchmark for evaluating the performance of qubits or quantum computers. And then the metric associated with that will be a fidelity, which tells us how well the gates or the unitary operations we perform in the system are coming out. So as most people might know, we have this set of backends or quantum processors in the cloud that we give access to general public, and along with the hardware, we have this open source software stack which is called Qiskit, and anybody can register and download it and start interacting with our quantum computers. So the main goal of this software stack is to provide a standardized interface between the user and the machine in a way that you can interact directly through this language called Quasm at the gate level, and you can even go at a lower level and interact with open pulse at the pulse level, in which you can define different gates with a variety of pulse definitions and so on. So this will give the user a lot of versatility in how to interact with these systems and how to run different kind of experiments and benchmarks, for example. And there are 4 elements that deal with different aspects of the software, but the most relevant for this talk is what we call Qubit Ignis, which deals with noise characterization and benchmarks of our quantum computers. So you can see some of the protocols I will discuss today implemented already in Qubit Ignis, and you could run it in some of our backends. So this benchmarking kind of hierarchy can be pictured a little bit like I'm showing here in this pyramid, where you can imagine different access levels to the device having different metrics associated with them. For example, for the case of superconducting qubits, which is a particular case of qubits that you can come up with, you can imagine when you fabricate them, you fabricate them very much in the same way that you fabricate silicon transistors. Once you have the system fabricated at the fab level, you will have something that comes out of that, which is like your T1 and T2, the interaction between the strength interaction between the qubits. I will talk a bit more about what all this means later. You can have some particular readout fidelity, which has to do with how strongly you couple your measurement apparatus to the qubits, some crosstalk levels, and so on. And then from there, you can imagine, okay, so now I have my system, and I'm gonna calibrate my set of gates, which should comprise eventually a universal set of gates for universal quantum computation. And then when you calibrate all those gates, you have many choices in the parameters you use, and many choices in the pulses that you use. And again, I will talk a bit more about this later. But then you have the next step in the hierarchy, where you have a set of benchmarks here that tell you about how well your gates perform, what is the dependence on calibrations, and so on. And then at the top of the pyramid, you have something that we call holistic benchmarks. And these benchmarks, they exist there because as you increase the size of the system, the gates that you have calibrated and that will comprise the different pieces of your algorithm, they have to perform well in conjunction with everything else in the circuit. And we will see an example where the performance of the gates in isolation is not necessarily the same as the performance of the gates as a whole. So at some point, it becomes pertinent to ask the question: what is my holistic performance of my system, and holistic as a whole? How well my system as a whole performs for some particular purpose. So this is kind of the hierarchy, and as we go higher in the pyramid, the benchmarks become more complicated. And what is important is that the meaning of these benchmarks starts to be less and less clear. So when we measure a number, we need to be sure of what number means, and also what that number doesn't mean. So I will start with the device level metrics. Very quickly, what is a qubit? A qubit can be implemented in a quantum state with 2 different energy levels. And then from those 2 levels, we can constitute a basis. We can build any quantum state as a superposition with complex coefficients that can be interpreted as some amplitudes from where you can extract probabilities of measuring one or the other basis state. And these are normalized. And this is a very standard for a definition of qubits. I'm going to focus on superconducting qubits, obviously, which is the technology we are pursuing. And for this particular talk, I won't have time to discuss other platforms. But superdynamic qubits in particular, the idea is that when you have a superconductor, you have material that is essentially dissipationless. So if you put some energy in it, in principle, that energy will remain there forever. And you can build we have here on the left some LC circuit, but it is essentially a harmonic oscillator. And this oscillator will have equally spaced energy levels. And that provides impracticality for operating that as a qubit, because now you don't have two isolated systems that you can address. So we have to come up with some variation of this LC circuit, which could be like a capacitor and an inductor, obviously. And the way we do it is by using a Josephson junction, which is a dissipative and nonlinear element. It is the only one we know that is both dissipative and nonlinear. And with that Josephson junction, what we have is an insulator that is in between two superconductors, and the wave function has a different phase across that barrier, and there is a phase difference delta. And then what is interesting here is that the voltage across the junction is related to the time variation of that delta, and the current across the junction is related to a sine function of that delta. So that when you describe the junction as an inductance, you realize that it's a nonlinear inductance, and then the potential of your energy spectrum becomes nonlinear, and then you can isolate two levels. So that's the way we can implement a qubit, and we have to remember that there are other levels above. So it's not really a qubit as for example an electron spin will be. With only two levels, but we have many levels. But in principle, we operate this with the intention of only addressing two of them. Now, there is a variety of flavors in superdynamic qubits, and it all depends on how we distribute the energy between the different parts of the circuit. So we have a Josephson junction. The Josephson junction has a critical current associated with it, which is this IC, and then we have a capacitance associated with it as well, and we can add some capacitance as well externally to the junction, and from there we have some energy stored in the capacitors, and then some energy stored in the inductors, and we can build a Hamiltonian with these two different energies, which is very similar to the usual harmonic oscillator, where here we'll have the kinetic inductance, the kinetic energy given by the charge degree of freedom, and then the potential energy given by the phase degree of freedom, which is essentially the same as flux. I'm expressing it here as a flux. So when you have this will be essentially a representation of a charge qubit, because the degree of freedom we are choosing is the number of charges in this island. So we have a coupling capacitor to our Josephson junction, and then this is an island of charge. And we can control the number of Cooper pairs in this island by an external voltage Vg, and that gives us this degree of freedom Ng. That if we plot the energies as a function of this Ng, we see that they have this form, and the junction provides this avoided level crossing because of the coupling. So now, if we look at this, we see that there is a sweet spot here where we are first order insensitive to fluctuations in Ng, and this is important because this source is going to be noisy. So if we are kicked out of the sweet spot, we will have a variation in the frequency of the qubit. So the frequency is not well defined, and that will affect the coherence of the qubits. So this was one of the first implementations of superdynamic qubits, a decade and a half ago, and then from there, people realized that this was not enough to have good qubits. So if you plot the different levels of the qubit versus in the x-axis here, we have the charge. We see that this charge dispersion is very wavy. And this is for a ratio of the energy in the junction with the energy in the capacitor of 1. But as we increase that ratio, and we put more and more energy in the junction, and we can do that by, for example, increasing the capacitor, which decreases EC. That capacitor is shunting in parallel that junction. So this curve becomes flatter. And therefore, when we have noise in the x-axis, our frequency suffers less and less until it's essentially, we have a EJ over EC of about 50 or so, then we have essentially flat features in these energy levels. And that's good because now we are more insensitive to noise. And then the price to pay for that is we lose an harmonicity. So we see that the distance between black and red and blue is quite varying here, but here is kind of constant, and also is more similar. So we look more like a harmonic oscillator than we were before. But there's still some finite harmonicity, and we can still address two levels and use this as a qubit. But it's a bit more challenging. And the key question here is that this loss of harmonicity happens at a lower rate than the flattening of the curve. So we have a win in approaching in doing this method for building our qubits. And the qubit that we build that this way is called a Transmon, and it's a charged qubit with something capacitance, and this is the type of qubits we are using up to this day in our systems. So I will talk a little bit about errors. I will start with very little about coherent errors because they are very particular in the sense that no loss of information happens, but you are trying to make an operation on a qubit, and then you are not implementing the operation you want. You're implementing something different because of some error in calibration and so on. And this is correctable if you really know what your error is. So there is always a way of correcting that error. But there are some other errors that are called incoherent, where there is loss of quantum information. One of them is what is called the qubit lifetime, which is a relaxation time whereby the qubit relaxes into the environment at some rate gamma 1, which is 1 over the time constant T1. And that happens via a variety of mechanisms. And then there is at the phasing time T phi, which has to do with the relative phase between the 0 and the 1 stage of the qubits. That when you lose that phase phi, that information, what you are driving your qubit is towards a mixed state of 0 and 1. There is no coherence between the two states, and then your information becomes essentially classical. So you cannot exploit quantum information for quantum algorithms. So T2 kind of comprises these two kind of loss of information with this expression here, and I'm showing here one of the best ones we have, 500 microseconds or so on a single isolated qubit. And just to give you an idea of how we have evolved during the past decades, this is the coherence times in superconducting qubits from the turn of the century until kind of almost today. So we see that we have improved our coherence time by 3 orders of magnitude per decade, roughly, which is quite impressive. And the trend is still upwards. So we still think we can keep improving our systems in this respect. And I'm giving here on the right a series of breakthroughs that made this possible. That go from changes in the science of the qubits to better understanding of materials and other things like proper filtering of the lines and shielding of the radiation in the environment of the qubit. So as some examples of where some relaxation or T1 problems can arise for the transmons I'm discussing, there is some dielectric loss that is inherent to the material itself. So normally the problem is in the interfaces between the superconductors and the semiconductor that is the substrate of the chip. And there are different interfaces. You have the substrate to metal, this substrate to air, and the metal to air, and then there is the bulk. And normally the surfaces is what we have found give the most issues because of different disorders in the fabrication process. And one way to mitigate that is to simply making your qubits larger. It will make the energy, the fields to be contained in the substrate, which is less worrying than the interfaces. So that's one way we have been trying to improve our coherence times. Another, of course, is to come up with better combinations of materials, of superconductors and semiconductors, and that's always an ongoing effort in research. Another example is, as we have in this picture, is that the qubits will, the chip that contains the qubits will have some particular size, and that size will have a natural resonant mode. And for some particular sizes of the chip, you will have that mode at a frequency that starts approaching the frequency of our qubits, which is about a few gigahertz. And there are some modes that can be like a slow line across the resonators that we use to read out or drive our qubits, and we can try to pin that mode by you can imagine a drum vibrating. If you press it, you kind of stop the vibration. We can do that by adding these wire bonds here that make these surfaces equipotential, essentially. So this is an example of something we did maybe 6 or 7 years ago. This is a very preliminary example of this. We do cleaner solutions these days. And then finally, there is this quasi-particle dissipation, which is you have radiation coming from the environment at some elevated temperature, let's say a Kelvin or so, where our qubits operate at tens of millikelvin, and then that radiation can break a Cooper pair, and then those quasi-particles at that ampere can dissipate energy and take it away from the qubit. So we normally wouldn't be worried about these quasi-particles because of the temperature, but as I'm saying, there is this aspect of radiation that might trigger the creation of quasi-particles. So we need to be careful on radiation for our qubits. So just very quickly, I'm going to say about dephasing. So T1 normally is it comes with the device, like the qubit itself, how it's built, how it's fabricated, will have some inherent T1. There is some aspect of it that relates to how you mount it in the fridge. But T2 is very in our transmons is very dependent on the on the configuration of the fridge where we cool down our qubits. And for that, we need to make sure that we attenuate all the input lines that we have, so that the photons, the noisy photons from thermal radiation arriving at the qubit are as few as possible. So we attenuate at every stage of the fridge, and then in the output we cannot attenuate because we want the signal to be the readout signal to be as high as possible, and the signal to noise ratio. So we use quantum limited amplifiers, which could be TUPAs or JPCs or things like that, and then we use higher amplification at hotter states. But the key amplification is here, the quantum limit amplification at the mixing chamber, called as a stage. So we normally, when we are very careful with this setup and we make sure that everything is cold, then we can attain kind of like T1 equals T2, where the bound, the ultimate bound of T2 is 2 T1, but we normally get T2 equals to only one time T1. That's for the device level metrics. It's very simple. We have like qubit related performance, coherence, and so on. There are more I don't have time to talk about, which is like something like crosstalk and coupling and readout fidelity and so on. But I will talk about the device, the subsystem level metrics, which involves a qubit or several qubits and the operations we run on them, the gates we run on them. And this is a bit more interesting. We start seeing some metrics that are quite interesting. So briefly, I will say how we run our single qubit gates. We apply microwave pulses of a particular frequency, which is the qubit frequency, which in our case tends to be around 5 gigahertz. These gates are about tens of nanoseconds long, and then we can control the axis in this block sphere here, where you have 0 and 1 at the poles. You can control the axis of rotation of the qubit state by changing the phase of your signal. As we can see here, in the blue and the green will be rotations around X and Y respectively, with a difference of phase of pi and 2 in each case. And we apply these gates to in this case, a resonator that can be also used to read out the qubit, or we can apply to a dedicated port that only drives the qubit gate. So this is what we do, single qubit gates for the X and Y. For the Z is a particular interesting case because all we are doing when we do a Z rotation is we are changing the labels of X and Y. So we just can't change the phase of subsequent pulses, and that implements a Z gate in 0 time. It can be Z90 or it can be Z of any angle. A Z90 will simply switch X and Y, and then X will become, so Y will become minus X and X will become Y. With this kind of Z gates, the nice thing about it is that we can implement it with essentially no error and 0 time. So our basis normally tends to be as heavy as possible in Z gates, and then as light as possible on X or Ys. Essentially, you just need X's because you can define the Y in terms of X's and Z's. Another thing here that is important for single qubit gates is that, as I said, our qubits are not qubits. They have many levels. And when you apply a tone to address the 0-1 transition, you kind of like are off resonantly driving 1 and 2, which changes its frequency a little bit. So you have a little bit of dephasing just because you have many levels. And then also another error that you could have is that you are trying to make it an excitation from 0 to 1, but it can end up in 2 or higher levels. So that kind of problem exacerbates when you try to make your gate implicitly shorter. So what we can do is we can try to run our gate by adding a pulse here that in the other quadrature. So if we are doing an X gate in the blue here, this will be in the Y quadrature. That is the derivative of this shape, which normally we use a Gaussian. So here is a Gaussian. This is the derivative of a Gaussian with a scaling amplitude factor, alpha. And then we calibrate this for better for the ideal error in our gates, depending on whether the error is dominated for 1 or 2 here. Phase errors or leakage will have different results in our calibration. These papers talk a little bit more about this technique, which is called drag, and we use this to be able to make our gates a bit faster than if we just had a Gaussian pulse. And then for 2 qubit gates, there are a number of interactions you can exploit. And in the interest of time, I'm gonna only talk about this one, the cross resonance, which is what we use in our all deployed devices throughout our fleet of quantum computers for all of them. And the idea of cross resonance is that we are using qubits that are fixed in frequency. We don't have a flux tuning of the frequency of the qubit, which will open a degree of freedom for flux noise, which is hard to deal with, although other superconducting qubit groups actually do have that flux tunability. We chose to use fixed frequency qubits, and for that you need a gate that is actually able to create interaction between the qubits with no moving parts. Let's say, like in this case, we are just applying a cross-resonant tone to the qubits, and that cross-resonance tone is going to trigger the interaction to start. Before that, the interaction is very weak, but as you increase the amplitude of that tone, you increase also the interaction between the qubits, and that creates entanglement. And the reason that happens is because we are coupling the qubits with a bus that provides a J factor, which is an XX kind of interaction, and this bus, which is a coplanar waveguide resonator, for example, will kind of alter the nature of each of the qubits, and each of the qubits gets a little bit of the flavor of the other qubit. And then when you apply a tone at qubit 1, let's say at the frequency of qubit 2, that creates qubit 2 to rotate in the blogosphere in a direction that depends on the state of qubit 1. So for example, in here, this is oscillation on the target qubit, when the qubit, the control qubit is in 0 or is in 1 for blue and red. And if you evolve this for enough times, you see a point in time where they are in opposite in opposite phases, let's say, and that kind of constitutes a C naught, which is a control NOT gate, which is fully entangling. And we just need the additional single qubit rotations to get a pure C naught from that. I think, because I have not a lot of time, I'm going to run through this. But basically, we have a variety of pulses that we can implement for this C naught gate that clean up the Hamiltonian of it. So we have a Hamiltonian that normally has this kind of C terms and IX and CX. And the one we want is this CX, because this C is for the control, this X is for the target. The X means a rotation about the X axis, and the C means that the direction of that rotation is determined by the sign of the control qubit. So we have a possibility of each direction depending on the control qubit. But we have these other terms, and we want to isolate this CX term. So what we do is we implement some pulse protocol, some echo protocol here, where we have the cross resonance in different signs that cancels every term except for the CX, and then we can reach fidelities of the order of 98% in 300 nanoseconds or so. But then we see that sometimes what we have, if we do tomography on the target qubit, sometimes we have components that are not purely X, CX or IX. We have some Y as well, and that is a problem. In this case, for example, we can see as we increase the amplitude, this IY keeps increasing, and what we can do to fix that is to add a concurrent pulse to the target that will kind of cancel that IX pulse, and then that will, if we see here the evolution of the target qubit in the blogosphere, we can see that with the cancellation is smoother, and we can make the gate essentially much better by canceling that IY that is not in the Hamiltonian we are interested in. And in this paper shows actually the first 99+% two-qubit gate that we demonstrated a few years ago. So now to go into the metrics that I was saying at the beginning of the talk, now that we have all these tools of running single two-qubit gates, we can ask how good are our gates, and the way of there are many ways of assessing that question, and if you see here some methods that I'm showing, probably the most comprehensive will be doing full process tomography, but that scales very poorly with, as your system grows in size, you will have a problem with the exponential growth of the number of experiments that you need to do. So what we're trying to look for instead is some protocols that will give us some information, even though it's not the entire amount of information you can extract from the system, but that still we can interpret as some kind of fidelity. And here in the right, there are some protocols that are a bit more scalable when you grow the system size. They don't grow exponentially. So I'm going to focus on randomized benchmarking because it's very versatile and very useful and reasonably easy to run. The philosophy behind randomized benchmarking is to use a set of gates to probe your system that are within some particular group. This group is not a universal set of gates. You cannot perform universal quantum computation with this group. And in fact, there is this Gottesman-Mill theorem that says that if you only use Clifford gates, which is the name of this group, you can simulate efficiently with a classical computer your system. But still, we can use this group to probe the noise of our system. When we use something like stabilizer codes for error correction, we essentially almost only use Clifford gates. And so they are useful. And the other nice thing about this Clifford group is when you twirl over it, when you run repeated random sequences of these elements, then it makes all the noise look the same. So the noise becomes what we call depolarizing, and we don't need to be worrying about what kind of like noise source we are having for getting a good fit of this evolution. So the way we run this is we take an n-qubit system and we run all these gates in green here, which each of them is an n-qubit Clifford, and then at the end we run a gate that is the inverse of all the previous gates, so that if you run all this circuit, you will be trying to implement the identity gate, and then you measure. And then once you measure, you will observe a decay on each qubit that goes from this is the probability of the qubit being at 1, and then it will decay to 0.5 as the noise it makes each of the sequences fail more and more. And then you can fit this exponential to a model like this, and from this alpha, taking into account the dimensionality of the system, you can get an error that you can associate with the error per Clifford. And each Clifford is comprised of different single and two qubit gates. Normally, that's one of the implementations we can use. And then from there, if you have an average number of two qubit gates per Clifford, and you assume that your noise is more or less well distributed across the gates, then you can get some feeling for how faulty are your single and your two qubit gates and so on. So as I was saying, another nice thing of the Clifford is that when you increase the system size, they increase exponentially, but the sampling difficulty doesn't increase exponentially, only polynomially. So we can still efficiently sample that set of Cliffords randomly to come up with the sequence that we need to run. So normally we do 1 and 2 qubit Cliffords only, and from there we get single and 2 qubit gate fidelities. But here is an example where there are protocols that are more holistic in a sense as we go up in the pyramid that might give us more information than the previous tier of the pyramid. So in this example, this is an example with 3 qubits where we have all-to-all connectivity, and we want to compare. We want to say, okay, if I benchmark the 3 2-qubit gates that we have in this triangle, and then I benchmark all the single qubit gates for the 3 qubits, could I predict the performance of the 3 qubit randomized benchmarking that I will get if I run 3 qubit randomized benchmarking, right? So the idea is that you take the sequence of experiments, you perform 1 and 2 qubit, and you perform 3 qubit RB, and then you look at what the prediction for 3 qubits is, and what the prediction from 1 and 2 qubit is, and what you actually get from the 3 qubit. And if you remember in the pyramid before the subsystem metrics, we had this layer that was calibrations, and actually calibrations matter a lot. How we calibrate our system is going to determine how it performs in different metrics. So in this case, we are going to look at 2 calibrations. In calibration A, we are calibrating the frequencies of the qubits all at the same time, and in calibration B, we are calibrating each qubit individually. So these qubits, they have CC interaction that I'm calling here as CC, and that means that the frequency of each qubit depends on the state of the neighbor to which is coupled. So when you calibrate all the frequencies simultaneously, you are kind of distributing that error over all the system, and you're making essentially that error a bit lower when you operate the system as a whole. Whereas if you calibrate each qubit independently, then when you only operate that qubit, it's going to do very well. But when you operate it with the neighbors, it's going to do much worse. And you can see this in these curves here, where the red curve, which is 2 qubit randomized benchmarking, does much worse when you are doing the separate calibration, because you are assuming with that calibration that the qubit is isolated, where that's not the case. So with these two calibrations, we can go and benchmark our single and two qubit gates, as stated here in this table. And then from here, we can predict the 3-qubit, what we will get for 3-qubit RV. So for calibration A, we should get like about 11%, 11.5%, and then nearly 20% for calibration B. And that's expected because calibration B assumes that each qubit is isolated where they are not. But now if we actually run the experiments, we see that for calibration A, we do indeed get around 11%, but for calibration B, we get much worse results. So this is telling us that there is something in 3-qubit benchmarking that is not captured when we only do 1 and 2-qubit benchmarking. And if you extrapolate this to large systems, then if somebody tells you here is a 20-qubit system with single qubit gates of this fidelity and 2-qubit gates of this fidelity, it makes you wonder, if I use all those single and 2-qubit gates as part of my 20-qubit system, are they still going to perform to this level of fidelity, or they're going to be worse? And chances are that they're going to be worse. So with that in mind, we want to look at holistic metrics, and this will be the last part of the talk. And we want to try to come up with a protocol that actually tells us how a given size system will perform in some kind of quantum protocol, which we want this to be as universal as possible. So we are going to get a number, we are going to get an answer, and we want that answer to be as informative as possible. So as we were saying, for the randomized benchmarking, the fact that you have random circuits is normally very useful, because it kind of treats the noise in an equal level. So we want to run these random circuits, and this is a metric that is called quantum volume that we defined a few years ago. And we want to run families of circuits that are increasingly large in our system, and we want to see how well they perform, and as we make the system and the circuit larger. And the 5-second summary of quantum volume, what is quantum volume, is the largest square circle that we can successfully run in our quantum computer. A square means that you have equal width, which is number of qubits, as depth, which is what I'm showing here as a set of 2-qubit unitaries. And what it means by successful, I will discuss in a minute. We want to give a number which is what is the largest square circuit, and we want to focus on square circuits because you could imagine an example where you have a 50 or 100 qubits a quantum computer, and then you focus on 2 or 3 qubits that you can run. They are very good compared to the others, and you can run for a long time and with a lot of gates. But that doesn't give you a sense of the power of the quantum computer, because you are leaving on the side a lot of qubits not exploited properly. And on the other side of the spectrum, you could have a system that has 1,000 qubits, but basically you can only run one gate on each of them. So that's very wide, but not deep. So we want to find the optimal medium, which is like growing your system size in the terms of number of qubits, but also in the terms of how many gates you perform for that number of qubits. So the circuit structure that we use is kind of defined here, but it's a bit simpler than this picture shows. What we are trying to do is, at each step, we choose randomly within our system size pairs of qubit. We pair each qubit randomly with another pair, and then we run a 2-qubit unitary between that pair. The way we do it in a system that has some local connectivity, where not all qubits are coupled to all of them, is we do this green part is a random permutation of the qubit labels, and then we do this unitary between neighbors. And what will happen in superconducting qubits, for example, where as opposed to ions, we don't have each qubit coupled to all the rest, is that we will have will need to run a circuit where one qubit needs to be coupled, it needs to be run with a 2-qubit unitary to a qubit that is much farther away. So in between, you need to couple to neighbors and then do swaps, which are quite costly in terms of like circuit depth. So so here, this quantum volume will have into account things like a number of qubits and the depth, but also the connectivity. When you have more connectivity, you don't need to do all these swap operations. And then when you have more gates in your set that you can physically implement in the qubits, then you have an easier time implementing these U operations. And then also, of course, there is the compiler and at the classical computing level, where when you want to run a unitary, there are many ways to do that. With the gates that you have at your disposal. So the compiler could do a really great job at reducing the amount of physical gates you run, or could do a terrible job at giving you a circuit that is much deeper than you need to implement. Okay, so once you have these circuits ready to run, then what you need to do is to understand. This is basically what I was saying, but you need to understand what it means to be successful. And for that, what we can define is this thing is called as the heavy output. So we for each circuit we simulate with no noise. We extract the ideal outcome of that circuit, and we can do that with our computer, with our laptop or whatever, and then we take all the probabilities for each bit string, and we order them in increasing probability, and then we take we take the median, and everything that is above the median we label as heavy output. So whenever we sample one of these circuits and we get a bit string that belongs to the heavy output, we make a tick and we say a heavy output was sampled. And then we do that repeatedly, and eventually we want the heavy output probability to be above 2/3. The ideal case with no noise will give you a heavy output, and if you run circuits that are deep enough, you have a distribution that is called Porter-Thomas. You will have a heavy output that is of the order of 0.85. So between 0.66 and 0.85 is the window in which we want our we need our computer to perform so that we can claim success. And then once we have a given output for a circuit and with some heavy output, this slide is basically saying that we are going to choose the largest square circuit. So for each number of qubits m, we look at the depth that we can get for each set of m within your big system, and we look at the max depth for each of them, and then we look at the minimum between that number of qubits and the maximum depth. So that's what it means by a square circuit. And then within that set of square circuits for different number of qubits, we look at the maximum. So if you can do 3 qubits with depth 3, but you cannot do 4 qubits with depth 4, we stay at 3, and then the quantum volume will be 2 to the 3, which is 8. Now this is how we get the heavy output. So we have our circuit can be described by a unitary matrix, and then which applies to all the qubits being in the ground state, and then we pass it to a classical simulator. We get a state vector out of that, and then we plot the probabilities from that state vector into the basis of choice, which normally is the C basis for our n qubits. And this will be an example. Well, this is what we will expect from a simulation that we will be sampling for a particular circuit. Now we sort it in increasing probability, and we define the median, and then any bit string at the right of the median is going to be heavy output, and any bit string on the left is going to be not heavy output. So what we do then is we take this one, for example, 0010, that is heavy output, so that's good. This is not heavy output, so that's not good, and so on. And then we start sampling our quantum computer. We get heavy outputs, we get no heavy output, and then as we keep sampling, we build a probability of sampling a heavy output for a particular circuit. And then we need to do this for many circuits. For in this case, we'll have like 0.69, so we'll have passed the test of the heavy output for this particular depth, a number of qubits. So the entire quantum volume protocol is we pick a random circuit, we pass it to the simulator, we get a set of probabilities, then we measure it in the quantum computer, and then we get the heavy output. And we want to do this with a number of circuits, like because at the end you're going to have a bimodal distribution between heavy output or not heavy output. So we want a number of circuits that is defined as minimum of 100, and we want to pass this heavy output threshold with a 2 sigma confidence, right, which is 95%. So you want 2/3 above heavy output probability, higher than 2/3 plus the 2 sigma. So as you increase the number of circuits that you run, your 2 sigma, your sigma will be decreasing. And this is an example for quantum volume 64 that was measured last year, where in the x-axis we see the number of circuits. Each of these circuits has a heavy output probability that is a blue dot. And then the black is the threshold that we are hoping to beat, and the red is the cumulative average of the heavy output. So we see that as we go in number of circuits, we are always around 0.7, but the 2 sigma interval, which is this pink shadow, is not beating the threshold until we get to about, in the inset here, about 750 circuits, more or less. And then at the 750, we can claim that we have had heavy output. This was 64, so therefore was 6 qubits. So we got quantum volume 64. It could be that you keep increasing the number of qubits and your sigma never reduces enough so that you can claim success. So then you will stop in the previous step for the quantum volume. So so far, since we defined this and we started looking at our devices for quantum volume, we have improved it by quite a bit, and we aim at doubling every year, and we have been doing so for the last 3 or 4 years, basically since we defined the metric. And this here shows the number of systems for which each quantum volume is attained as a function of the year. And in last year we had Qubit 64 for one of the systems. And the improvements that we had for that were coming from many fronts. One, of course, was getting better devices. Having devices with lower error rates helps a lot. Better readout fidelity helps a lot as well. Interestingly, in this Qubit 16 improvement, this Johannesburg backend was less connected than the connectivity was lighter than the Tokyo, and even though that can be seen as a problem for the swap implementation I was commenting before, it comes with an advantage that we have less crosstalk because each qubit has fewer neighbors, so that ended up being a winning characteristic of this other backend. Another thing that we normally do for improving the quantum volume is that once you have the unitary you want to implement, you could choose to implement a slightly different unitary that has fewer 2-qubit gates, which are the main source of error in our systems, and you're going to pay the price in that the final result is not going to be the exact result on the distribution that you sample out of your circuit. But if it's close enough and you can win by having fewer 2-qubit gates, it's advantageous to actually do that and not implement the one that the protocol requires, but something that is approximate. So that we do as well. And then there are some tricks of mapping each qubit in the real device to the abstract qubit that the protocol is calling for, depending on the connectivity of that particular subset of qubits. So there is all these improvements and all these tricks that we did, and all these tools are really useful in that. Once we think about the metric beyond simply being a metric, but actually being a proxy for how a quantum algorithm would look like, if you are going to have some VQE kind of algorithm where you have a series of gates of some depth, and you want to implement them as well as possible. All these tricks that we are playing here are really useful in that case as well. So improving the quantum volume actually help us come up with better implementation of our algorithms. And finally, this is our recent result just last December, where we implemented we reached quantum volume 128 in the same device where we had 64. So I was gonna talk a little bit about something that is not quality of circuits, but we are at the hour. I was gonna talk about variety of circuits, but we could stop here, or I could talk about that. I don't mind. I don't know what do you think, David? Or if there are any questions, I could address them.
So if you want to say a few words, I mean, you were in a hurry, but if you have time, you can.
I could spend 5 minutes maybe. Yeah. So I'm not going to go through the details of this following one, but this is a paper that we put out, I think a few weeks ago, 3 or 4 weeks ago, where all I've been talking about so far is quality of circuit. So when you have a circuit that you want to run in a quantum computer, how well can you run it, and how well the output distribution matches what you should be getting if you had no noise. But there is more than that, because you can imagine that quantum computers, if you had a perfect one, but it runs very slowly, if you can only run n circuits per hour versus 1,000x circuits per hour. That is something to take into account in performance of quantum computers, but also variety. Like the circuits I've been showing here are circuits that are a series of gates followed by a measurement. But there are algorithms that have a very, very different structure, where you will have a series of gates, you will have measurements in some of the qubits in between those gates. And then based on the results of those measurements, you will have different parameters in the subsequent gates in the circuit. So that brings a very high, a very strong complication in running the circuits, because now once you measure the qubits, the result has to go out of the system. It has to come and be analyzed by classical electronics. That set of classical electronics has to make a decision on what the result was in a time that is shorter than the coherence time of your qubits, and then send further instructions back. So what we did for this, and I'm not going to go through this, but we basically implemented 2 versions of quantum phase estimation. One version that I'm calling here iterative phase estimation, which is like the round symbols, requires that you extract the bit of the phase you are trying to estimate within the circuit you are running. So you only run one circuit, and you have measurements in between. And then the other protocol, which is from Kitaev, the original quantum phase estimation protocol, it just runs the circuits, and then you can analyze the results on the side at a later time. So you don't need all this kind of like real-time computing. You don't need classical electronics that can measure your qubits and apply conditional operations within the lifetime of the circuit. So that's much easier. And we obviously we know in this right plot here, as by resources here, I'm meaning measurements, physical measurement of qubits, and I'm allowing the user to measure the system more and more. These 2 implementations of quantum phase estimation converge. One is not better than the other. They all give you an advantage versus classical means. But if I restrict the user to a few measurements only, so I say, and this makes a lot of sense also in the sense of what I was talking about capacity, like how long do you need to run the quantum computer to get a result that is satisfactory. So if we limit the number of resources, the iterative phase estimation, here for each color, I have a different number of resources. It gives a tangible advantage versus the Kitaev original approach. And this iterative one is actually exploiting what we call real-time compute, which places a lot of demands on the classical electronics that we use to control and read out our systems. So now we can consider quantum computers are not only the quantum hardware, but they are also comprised of all the control electronics and all the readout and all the software that goes with it. So this is out in this paper that we put out recently. A lot more description of this, but this goes a little bit beyond these metrics I was talking about. It's not enough to have good quantum computers, but we want also some of the tools that make all the performance a lot more versatile for different structures of different algorithms. So I think I'll just finish with that. I will leave the conclusions there, and maybe if there are some questions, I can address them.
So thank you very much. I know that you are in a hurry, so I'm going to get quite fast with the questions. Okay, just maybe a couple of them. So at the very beginning, I read that you show some plot about the increase in how T2 is increased along the years. So this is not linear, right? So there's a kind of saturation, or what do you think?
Yeah, that is not linear. Let me try to go to that. Trying to see. Yeah, so it eventually. So there are two aspects of this. One is at some point, I think there will be a slowdown on the progress. Because because there I mean, every time we improve, the next improvement is harder, right? Because so this is it. So you could argue that, you know, maybe this is gonna start flattening at some point, right? And maybe there are signs of flattening already. And each improvement is harder than the previous one, because we are looking at systems. When the system becomes more coherent, is more sensitive. It's more sensitive to everything in the surrounding. So we need to make everything better for the same improvement, and not just better, like increasingly better for the same kind of improvement. And at some point, this is going to stop. Like we are gonna reach the limit for this particular implementation of qubits. There are many other implementations that live in a completely different scale of coherence, but also in a completely different scale of gate fidelities and gate speeds and so on. But the thing that we have to bear in mind here is that we are doing this with the hope of reaching the threshold beyond which quantum error correction becomes feasible. So if we hit a threshold with some significant overhead, but we need to reach that, we need to beat that threshold by a good margin. At that point, quantum error correction theory tells you that you can make your qubit arbitrarily good by increasing the size of the code. So you will have a logical qubit that is comprised of many physical qubits. And if the physical qubits are good enough, so if we are in this plot above some number, I will tell why that number is not clear. Then just throwing more physical qubits at the logical qubit will make the logical qubit better. So that's what we need. Now, this, what I call threshold, or how good we need to be, is based on theory simulations and theory arguments that treat the noise as a simplified model of some type of noise. And we know that in reality, the noise is very complex and has many different sources. So it's difficult to say we need to be at a millisecond or we need to be at 100 millisecond coherence, because that's going to depend on a lot of more things. It's going to depend on what code you choose, what kind of crosstalk errors you have, and what kind of readout you have, and so on. So it is hard to put a number on what will be enough, but there will be one point where hopefully we will reach a point where we are good, and we don't need to put a lot more work in improving this.
Okay, so I can do two questions, right? Two fast questions, maybe.
Yeah,
So
that's fine.
one is, what is more important for increasing quantum volume? How the physical systems are wired, superconducting versus ions, for instance, or how the algorithm is built?
So the ions have a huge advantage in that they have all-to-all connectivity. And if you look at Honeywell, which is a team that has ions as quantum computers, they have been matching our quantum volume, although we have had this recent result on 128. But the issue with connectivity is that it also brings the crosstalk issue to the stage, right? So it's much easier to have crosstalk. So I guess the question, what is more important, is difficult to answer, because it depends on what tools you have at your disposal. If you have a compiler that is really smart, if you have a way of making your qubit, your circuits efficient with fewer connections, then it's more important to follow that route and try to build a system that is lower connectivity, and then have the compiler play around that. Of course, in the ideal world, you will find a way of canceling the crosstalk and dealing with it in a proper way. So you can have the best of both worlds. You can have high connectivity, low crosstalk error, but that is ongoing research, and possibly some of the improvements in quantum volume will come from actually managing crosstalk better and letting us increase the heaviness of our connectivity.
And thank you, Antonio. And a last question is, you explain about the connectivity between the two qubits via quantum bus, something like this. So I mean, in IBM, you are using a fixed coupler, or you are using a tunable coupler?
We are using a fixed coupler. There is no tuning frequency anywhere in the deployed device. If you look at our publications over the past few years, we have put work out that was based on tunable buses, right? Where we implemented an ISWAP using a tunable bus, and what we do is we drive that bus with a parametrically at the different of the frequency of the qubits, right? And with that you can create entanglement, and that is something that is one part of research is still looking for other methods of building our systems. So we are a research group, so we don't keep any option closed, but at the moment none of our heavy efforts in deployed device has any tunability anywhere.
So the qubits are always coupled.
They are the qubits that are coupled are always coupled by a fixed frequency bus, right? There are qubits. If you look at the topology of our system, there are qubits that are coupled to some neighbors, but there are some, like, not all qubits are coupled to all the qubits.
Yeah. But the ones that are physically coupled, they are always coupled, right?
Yeah. Right. There is a finite, I understand the question. There is always a non-zero amount of coupling between them. Yeah, and you can increase that coupling with the cross resonance, but the fact that there is a non-zero coupling all the time means that that ZZ problem I was saying is always there. We always have a finite ZZ by virtue of that coupling that is never zero.
And this is not a problem for scalability. I mean, because at the end, if you are going to put more qubits that they are always coupled, I don't know, you are going to have this, as you explain us, when you benchmark the errors, that when you drive one qubit is affecting the other, and so on.
Yes, if we didn't do anything else, there is always a source of error that is at any given time in a circuit is active, is creating an error. But there are ways to deal with ZZ in a way that you could have coupling that is non-zero. But as I was saying, I said this very quickly, but during the slide of coherent errors, ZC is a coherent error, so you should be able to cancel it if you do it smart. So it is very hard, it's very complicated, but we believe it can be done. So as you increase your system, all this non-zero coupling is going to be present, but you can play tricks with your pulse sequence and doing some kind of echoing and things like that. That it will increase the complexity of what you do, but it will make the system look much better. So yeah, I mean the other approach that probably you have in mind is that you could have the coupling being tunable, like what Google does, where you have the two qubits are not talking to each other until the moment you do the two-qubit gate, where you tune them in and then right.
And you need an extra ancilla. You need another qubit.
Right. You have a higher overhead in the footprint of your system. You need more qubits, and there is and there is also this this issue of like also crosstalk while you do the sweeping and things like that. If you are going to move the qubits on frequency, if you are just going to use the ancilla to couple, then you need to tune the ancilla as well, which anytime you tune a qubit in frequency, you run the chance of the qubit going through an error, because there might be some two-level systems that are noisy in the neighborhood of the spectrum of the qubit and things like that. So it's the usual. You have to pick your poison, right? We chose to do everything at fixed frequency because we don't want to open the flux degree of freedom as long as we can afford it. And then that comes with the complication of having all these interactions that are non-zero, right? But if you look at the overall fidelities of our gates and other groups with tunability, they are very similar. The origin of the errors is different, but the overall quality of the gates are very similar.
Okay, so thank you very much for the nice talk. It was really a pleasure, Antonio.
Okay, thank you.
Thanks a lot, Antonio.
Okay, bye.